subtopic number 2, which is on induced EMF. Okay, so in this subtopic, you have to be able to explain induced EMF by using the Faraday's I don't know how to pronounce it. Faraday's experiment, state and use Faraday's law, and state and use Lenz's law to determine the direction of induced current, and lastly, apply induced EMF in a straight conductor, a coil, and a rotating coil. Okay. Electromagnetic induction. So what is it? It is the production of induced EMF. So they produce induced EMF ataupun induced current when there is a magnetic flux through a loop, coil ataupun a circuit is changed. So basically, when there is a changes of magnetic flux, they will produce an induced EMF ataupun an induced current. Okay. Kalau dia tidak changes on the magnetic flux, dia tidak akan ada induced EMF ataupun induced current. So the meaning of magnetic flux is there is a relative motion of loop and magnetic field lines. There is a motion between the loop, lepas tu the magnetic field lines cut lah. Okay, lepas tu the number of magnetic field lines passing through a coil can either increase ataupun decrease. I don't really understand why I wrote it as the meaning of magnetic flux. What do you mean the meaning of magnetic flux? Sorry everybody. Let me just refer back to the slides that I refer to lah. Okay. Let me just check. Oh, sorry. It is the meaning of changing in magnetic flux. Oh, okay. Right. I'm gonna basically redo it. I'm gonna do a correction here. Patutlah I don't understand. So the meaning of changes changes in magnetic flux. Okay, apa ni changes in magnetic flux? Macam mana dia boleh ada change? Basically, dia ada change because there is a relative motion of loop. So, bila loop to keep on moving, dia akan produce this induced EMF ataupun induced current lah, okay? So, the magnetic field lines ni, bila dia keep on moving, they are cut. Macam dia tercut-cut lah. Yalah, kan? Lepas tu, second one is the number of magnetic field lines passing through a coil are increase ataupun decrease. So kalau dia limpas satu magnetic field lines ni, because there is a motion between the magnet ni, dia akan either increase the number of magnetic field lines ataupun dia akan decrease the number of magnetic field lines lah when they are moving. Gitulah. Okay. So Faraday's experiment, what is this? So there are three. Basically these are the most important part lah. So I've summarized it down. So when there is no motion between the magnet and the loop, so kiranya magnet ni stay je macam ni, the galvanometer shows no deflection, so tiada akan ada pergerakan current. Okay, there is no induced current. Lepas tu, when the magnet is moved towards the loop here, it increases the number of magnetic field lines passing through the loop. So kiranya dia bergerak ni kan, dia akan lagi ada banyak extra lah lines ni. Okay, sampai dia masuk ke dalam kan. Lepas tu, what it do is it causes the galvanometer needle to be deflected, indicating an induced current is produced. Okay, so bila kamu ada motion macam ni, dia akan produce an induced current. So this is the induced current lah punya direction. Okay, alright. Lepas tu, when the magnet is moving away from the loop, it decreases the number of magnetic field lines passing through this loop. Actually, I should reduce the amount. Is it the same? It's actually the same, right? So basically, you just have to know that the magnetic field lines ni passing through this loop will decrease lah bila the magnet is taken away from the loop. So the induced current ni pula, dia akan bergerak in the opposite direction. Okay? Okay, lepas tu, so what can we get from this experiment of Faraday's experiment? From these experiments, it can be seen that the EMF is induced only when the magnetic flux through the coil change. Okay, So sekarang ni dia punya magnetic field lines going through the loop is either increase ataupun decrease. Okay, so that's why there is a change in the magnetic flux lah. Okay, lagi satu apa yang berubah is because the because there is a motion lah between the magnet and the loop. Itulah maksud dia the magnetic flux ni changing. Okay, so when there is no change in the magnetic flux pula, electromagnetic induction cannot occur. So macam ni lah, dia stay macam tu. So dia tiada presence of back EMF ataupun induced current. Induced EMF ataupun induced current lah. Okay, so induced EMF pula will increase when a stronger magnet is used because the magnetic flux will increase ataupun the magnet is pushed faster into the coil, and then you can either increase the area of the coil or the number of turns supaya kamu punya induced EMF lagi besar. Okay, alright, so that is basically Faraday's experiment. Lepas tu, a changing magnetic flux can produce an electric current and EMF, which is known as electromagnetic induction lah. Okay, so the magnitude of this induced EMF is proportional to the rate of change of the magnetic flux. Actually it should be like this. So if the circuit or coil with a certain number of turns, we can write the equation to be equal to this one. So an induced current will always flow in the direction that opposes the change in magnetic flux that causes it. So that's why there is a negative here. So it's basically telling us that the induced current will flow in a direction that opposes the change in magnetic flux that causes it. Okay. Alright, so how do you determine the direction of the induced current ni adalah kamu akan guna right hand grip rule. Okay, so your thumb here will be telling us the field, which is the north, and then the fingers will curl in the direction of current. Okay, so basically thumb points in the direction of magnetic field lines lah. So if you have a clockwise current, it will create a magnetic field that is going into the page, and an anti-clockwise current creates a magnetic field out of the page. Okay, so sekarang ni kita apply dia dalam kita punya this solenoid here. So when the solenoid moves towards the bar magnet, it experiences an increase in magnetic flux lah. So bila they experience a change in magnetic flux, there will be a current induced. So current ni sedang ada induced current lah flowing through this circuit. So based on Lenz's law, the direction of current induced should opposes the change. So maksudnya the right end of the solenoid ni mesti form a north pole to oppose incoming north pole of the bar magnet. So dorang tidak mau attractive force here, dorang mau repulsive force. So mesti bila the end of the bar magnet is N, di sini mesti juga N. Okay, macam tu lah. That is basically what Lenz's law is telling us. Dia mesti oppose the change. Okay, so the direction ni mesti the direction of current ni mesti opposes the change. Okay, so that is Lenz's law. So how do we use Lenz's law to determine the direction of induced current? So untuk kamu cari the direction of induced current ni, kalau flux decreases, you replace it. Oh, actually this one is a bit hard to understand, so I'm just gonna do this one. So for incoming current, you have to create same pole to repel. Okay, untuk incoming magnet lah. So sekarang ni kalau macam ni, kita mesti letak N juga. So for both ends ni mesti north pole. Contohlah kalau they recede pula kan, they're receding magnet, they should create opposite pole to create lah. So sekarang ni the N di sini mesti S kalau dia bergerak away from the solenoid. Kalau dia towards the magnet, dia akan jadi north di sini. Okay, so once you know the direction of induced magnetic field, you have to use right hand grip rule to find the direction of the induced current. Okay, alright. Next, we have induced EMF in a straight conductor moving in a magnetic field. Okay, so area of the loop increases as the movable rod travels to the right. So sini area ni increase bila dia bergerak ke kanan, causing a change in magnetic flux. Okay, so remember, whenever there is motion, there is a change in magnetic flux. So from Faraday's law, noting that the value of turns is 1, EMF induced is given by this equation here. So assuming that the rod assuming rod moves a distance dx in time dt in a certain time, we can substitute the equation to become like this. Okay, so it's gonna be equal to negative BLV. Negative ni sebab untuk lens law lah. Okay, so in general, the magnitude of the induced EMF in the straight conductor is given by this equation. So this is the equation that you are gonna apply untuk to solve a problem lah. Okay, so the direction of the induced current in the straight conductor pula can be determined using either Fleming right hand rule ataupun kamu boleh guna right hand palm rule. Okay, so untuk Fleming Fleming right hand rule, this is the thumb will be telling us the velocity, direction of velocity. Magnetic field is B. The pointing finger is telling us the direction of magnetic field, and lastly the middle finger is either the induced current. Okay, so that is the direction lah. Untuk right hand palm rule pula, the palm is telling us the direction of induced current, the fingers are telling us the direction of magnetic field, whereas the thumb is telling us the direction of velocity. Okay, so if we apply it into this diagram here, we will see that the induced current is moving this way. Okay, so kalau kamu apply guna Fleming right hand rule ataupun right hand palm rule, you will get that the induced current is moving anti-clockwise. Okay, lepas tu what else? Okay, so we have induced EMF of a coil pula. Tadi ni straight conductor, lepas tu sekarang kita tengok pasal coil. Okay, so for a coil, there can either be a change in the magnetic field ataupun a change in the area. So changing of B with time, we can let phi is equal to this one. So if B is perpendicular to the plane of the coil, theta will be equal to 0. So cos 0 is equal to what lah? So assuming that the area is constant, we will get this equation here. So this one I'm gonna add later lah. Actually, saya lupa belum tambah ni. So this is basically B final minus B initial over the time. Okay, basically like this lah, the equation. Lepas tu untuk bila there is a change in the area with time, just do the same thing but just let B to be constant. So this will be area final minus area initial divided by the time. Okay, so that is the two equations that you can use for induced EMF of a coil lah. So induced EMF in a rotating coil pula. Okay, so untuk bila coil is rotating, macam di sekarang ni dia sedang rotate lah, it is given by this equation here. So again, we substitute phi to be equal to this one, and we differentiate with respect to time this cosine omega t. We will then get this equation here. So negative cancel. We will then get the induced EMF in a rotating coil to be equal to this equation here. Okay, so n is the number of turns, p is the magnetic field, a is the area, whereas omega is the angular velocity lah. All right. Okay, so this is basically a sine graph lah. So the EMF induced varies sinusoidally with time. So this is an alternating voltage lah, sebab dia ada positive and negative value. So induced EMF will be maximum when sine omega t is equal to 1. Hence, the maximum EMF kita boleh guna this equation here lah, right? Where omega is equal to 2 pi f ataupun 2 pi over t. Okay, so the EMF will be equal to a maximum when the magnetic field is parallel to the plane of the coil and the rate of change of magnetic flux is at a maximum. Lepas tu EMF pula akan equal to 0 when B is perpendicular to the plane of the coil and the rate of change of magnetic flux is 0 lah. Okay, so that is for induced EMF in a straight conductor, coil and rotating coil lah. So let's apply this equation to this question here lah, example 3. So we have to calculate at what speed should the bar move to produce a current of 0.5 ampere in the resistor. Okay, so everything sudah kena bagi di sini lah. Right, so we know that for a straight conductor, the equation is BLV sine theta. So this is actually L because capital L is inductance. Okay? So kamu guna small italic L. Alright, so susunod untuk V, kamu akan dapat BL sine theta. This is EMF. So sekarang ni kita tidak the value of EMF. But what do we know about EMF? EMF is actually this, the voltage. So EMF can also be equal to IR, which is Ohm's law, V equal to IR lah. So kita boleh lah substitute di sini. Dia jadi IR. Sebab I pun sudah ada, R pun sudah ada. So kamu just substitute lah all the values. So you should get the speed of the bar to be equal to 2 meter per second. Okay? Alright, lepas tu apa lagi? What is the direction of the induced current? So sekarang ni sama juga. Kalau kamu tengok, this diagram is actually similar to this one. So kalau kamu apply this Fleming right hand rule ataupun right hand palm rule, it will be moving clockwise. Oh, clockwise pula. Tadi saya sebut apa? Anti-clockwise kah? Anti-clockwise macam ni. This is clockwise, ah. So the direction is clockwise. Basically clockwise dia tu maksud dia macam ni betul. Dia bergerak macam begini. So this is clockwise lah kan. Macam tu lah, right? So that is example number 3. Example number 4. We have a coil which has an area of 8 centimeter square. So area is 8 times 10 to the power of negative 4 meter square. Lepas tu D. Alright. Number of turns is 50. Lepas tu magnetic field is 1.8 Tesla. If the magnetic flux density is steadily reduced, so initial, then reduced to 0.6 Tesla in 0.02 seconds, determine the induced EMF. So that is just negative. And B final minus B initial over the time. So kamu akan dapat negative 2.4 volt. Right? Negative ka? Wait, 2.4 volt lah. Sebab you will get here negative, lepas tu negative ni jadi positive. Okay? Alright, example number 5. We have a narrow coil of 10 turns. Masih lagi coil lah. Area is 48 meters square, placed perpendicular to a uniform magnetic field of 1.2 Tesla. After 5 seconds, the area of the coil is increased to, so this is the final area lah, 83 meters square. So this is initial. So we have to calculate the induced EMF again. So that is negative and B, A final minus A initial. Divide by the time. So you should get the EMF to be equal to negative 84 volts. So again, negative ni just the Lenz's law punya lah. Dia akan opposes the change. Okay. Alright, so I'm a bit tired talking. Example number 6. We have a square coil of copper wire of size 0.075 meter. Has 25 turns, so this is basically area lah. Times 0.075. Lepas tu dia ada 25 turns. Placed in a uniform magnetic field of flux density 0.85 Tesla. And then the coil is rotated at a constant speed of 2 revolutions per second. 2 revolutions per second is omega, 2 RPS lah. About the axis of rotation, what is the value of the maximum EMF induced? So this should be in revolution. This should be in, oh my god, I don't remember. This should be in, let me just think. That it has been radian per second. Yeah, it should be radian per second. So 1 revolution is 2 pi. So it's going to be 4 pi radian per second. Okay, so apa formula untuk rotating coil? It is NBA omega sin omega T lah. Okay, so untuk maximum, apa yang perlu berlaku bila induced EMF is maximum? Sin omega T mesti equal to 1. So it will be NBA omega. Okay, so apa nilai maximum induced EMF? It will be equal to 1.5 volt. Alright, so that is example number 6. So yeah, that is basically our second subtopic.